here we go. So if you're watching the video here, maybe hit pause and look at how we did the warm-up. I forgot to record it, but go ahead and look at the warm-up. This was just a indefinite integral where we just found the antiderivatives. And everything was just doing algebra or using our rules or our facts that we've already known. Well, today we're going to talk about the fact that we know the fundamental theorem of calculus said you can undo an integral by using the antiderivative. And then all we have to do is put a plus c. And remember that plus c is there because it's like a family of functions. It represents all possible antiderivatives of that state. So, for example, here's a really quick one. Do remember notation, and that's one of the things I want to focus on. So if I have this, the integral from 0 to 2 of x squared dx, I have to write the antiderivative, and then I have to evaluate the bounds. And we usually put a straight line here. They use brackets. And then we have our answer, right? That was our definite integral. The indefinite integral is what happens if I don't have bounds. Then all we do is write with the plus c. Okay, so that's nothing new. We've been doing that. This is something that you may want to either take a screenshot of right now or refer to page 439 in your textbook. And we've made reference to this before. I'm specifically going to talk about one antiderivative that's a little tricky here as an example down below. But we have, if I don't have anything or just a constant, then that value is always x plus c. The antiderivative is x plus c. We know the power rule. We have the natural log antiderivative, e to the x. We have all the trig functions, and we have the inverse trig functions, which, by the way, on next week, we're going to do a lot more with these inverse functions. And then this secant one, we actually don't really use. So this last one, secant inverse, we don't really use that. Now, if you see something exactly the way it's written in this chart, right? Like let's say you saw the integral of secant squared dx. Well, its antiderivative is tangent of x plus c, right? We just write that answer, and we are undoing the derivative, but that's just, if you see it in the chart, you know the antiderivative. Okay, but what if we don't see it exactly in this chart? How do we deal with problems like that? And that's what I want to show you here. It's up to you if you want to write these. I want to just make note of a couple of ones that are a little more unique that we haven't done a ton of lately. Okay, so this first one here, directions are just evaluate the integrals, and it says use the chart. Maybe there should be parentheses around there. So what do I have? Well, I've got a 5. 5 times 1/2 to the power of x. That 5 is a constant multiplier. So remember, the 5 can be pushed out. And then I have a number raised to the power of x. Well, that number is the exact same spot or in the same location as the a value right here, a to the power of x. So this one is usually one that students kind of have a hard time with because it's hard to undo this derivative. So it's more of whose derivative gives me 1/2 of x? Well, it's the exact same thing. So notice a to the x, and then we're dividing by the natural log of a, which in my mind is the same as timesing by the natural log of the base, the reciprocal of that. That didn't turn out the way I wanted it to. I'm going to write that a little better. So I like to write it as timesing by the natural log of the base. Something's wrong with my pen. That still didn't turn out the way I wanted it to. Try it again. There we go. A little better. You can see it's times. And then it's multiplied by the 5. Well, if I'm going to put the 5 here, this 5 is actually going to be 5 over 1. So instead of putting the 5 right there, I can put the 5 up top. And then the last part is putting a plus c. So we do have to say, okay, if there's a multiplier, that multiplier can be pushed out, and then it's directly related to the chart exactly as is. So we just use the rule in the chart to replace it with what we want. Okay? And again, you could also write it like this. But it all divided by the natural log of 1/2. Okay, so same thing. All right, what about the next one? Well, notice I've got the square root of 1 minus r squared. And when I look over here, I've got the square root of 1 minus x squared. So this is definitely an inverse sine function, but that 7 kind of screws things up. Well, the 7 is a multiplier. So I'm going to pull that 7 out, and I'm going to just rewrite this as 1 minus r squared dr. And then I know that my answer is just taking what is the antiderivative of this. It's using the chart right there. So sine inverse of x. And then we always just put a plus c at the end. C stands for any constant. And there it is. If you're not sure, you can always take the derivative of your answer, and that'll get you right back to where you started. Okay, the last one here is just a little bit tricky. If you notice, there's two ways to think of this. In the bottom, each item has a factor of 4. So I could pull that factor out, and then we actually have a 1/4. So I'm going to pull a 1/4 out as a multiplier because 1 times 1 is 1, and in the bottom, 4 times 1 would just leave the 4 out here. And then there's one other thing I'm going to do. See how it's t squared plus 1? I can write that as 1 plus t squared because addition you can write in any order. And the only reason why I'd want to do that is now I know, based off of my table, the antiderivative of 1 over 1 plus t squared is the same as the inverse of tangent. So tangent inverse of x, actually instead of x here it would be a t. And then I would times that answer out in front by 1/4. And then we just put the plus c at the end. Okay, so that's how we can use this chart. And you should always be aware of a constant multiplier. I tried to put that in every one so we don't ever forget that. Okay, so my question to you then is what happens if it's not exactly in the chart? What do we have to do? And this is what the video from last week talked about. We have to do U-Substitution. All right, I should say video from yesterday. So we're going to do some ones that honestly you could answer these with guess and check. But we're going to focus on the U-Substitution. And yes, these are kind of easier ones just so you guys can get the process of it without getting really bogged down with the derivative or the calculus side of it. But you'll notice here that this 4 in the integral of cosine of 4x, that 4 is protected by the inner part of cosine. So I cannot pull the 4 out. That is not a multiplier. And that's unfortunate because I don't love that that is there, because if it wasn't, if it was just cosine, I could do that antiderivative pretty quickly. So what we're going to do is we're going to take the inside piece and we're going to call that u. Now it doesn't really matter that you use u, it's just most common. You could use any variable, but I'm going to let u equal 4x. So what that looks like now is it's the cosine of u, right? So we replace 4x with u, but then we have a problem. I don't have a dx, right? I need to replace dx with something in terms of u, because if I replace this with u, then everything in this integral has to be in terms of u. So as we saw before, I can then find dx by taking the derivative of u. That's like undoing the chain rule. This is the process. So I'm going to take the derivative of what I called u. Well, the derivative of 4 is 4 dx. Now, I want to replace dx with exactly what it's equal to, but I don't have an extra 4 in here. So I need to move this 4 over to the other side. And now, instead of writing dx, I'm going to replace dx with exactly what it's equal to. So some students like to do this, but notice that's a 1/4, right? So we're going to pull that 1/4 out. And what's left over is a much easier integral. And that's the whole goal. U-substitution makes our life easier. All right? So now I'm thinking, all right, well, whose derivative gives me cosine? That's sine of u plus c, and then the 1/4 drops down. Notice I didn't write the integral anymore because that's the answer. And then the last part is we don't like to have our answer written in terms of u. We want it written in terms of x. We got to go back to say, well, what was u equal to? It's equal to 4x. Now, before U-substitution, we never knew where this 1/4 came from. We had to guess and check, and that's fine for a problem like this. You could get the answer with guess and check, because if I take the derivative, I would have to apply the chain rule, and the derivative of this answer would have an extra 4 coming out. So the 1/4 will compensate for that. But U-substitution eliminates the guess and check, and it's our method for doing that. It's going to take a while for us to become really comfortable with this. That's why we're doing multiple problems today. So let's look at number 2. I have the integral of e to the x squared. Now keep in mind that's e to the x squared. And I'm going to give you a hint as to how you know what value you want u to be. Okay? U should always be an inner function if possible. All right, like here, the inside function was 4x, and here the inside function is x squared. So I know I'm going to have a du somewhere. So every time you write u, your next step is just to take the derivative of that. And remember, the derivative of x is dx. Now what we want to do, actually, I wonder if I can do this. There should be an x in here, otherwise this isn't going to work. If you can, sneak an x right here. I think I forgot to just write that in. So the original problem should have an x right here. Okay, now notice what we have. I need to replace, du is going to replace everything else. So it's going to replace the dx, which we have. It's going to replace the x. But I don't have an extra 2 here, so this 2 has to move over. And then what's left over is du is going to replace the x dx. All right, so now, how does this look easier? Well, I have e, and then I said it was e to the u, because x squared is replaced with u. And then the blue x and the dx is going to be replaced with the 1/2 du. But that 1/2 is a multiplier. So I would really just want to rewrite it. And you could just push that 1/2 out there right away. Okay. Now, once you get the hang of this, look at our new integral. Our new integral is much friendlier than the original, and that's the goal of U-substitution. So now we're thinking, whose derivative gives me e to the u? Well, the antiderivative of e to the u is e to the u. The 1/2 is just a multiplier, so that's going to stay. And then we put plus c. But notice our answer is in terms of u. We want it in terms of x. So all I'm going to do is take what u was originally and replace u with x. There's my answer. Now again, if you're not sure, let's take the derivative of it. Okay, if you take the derivative of this, you'll have to use the chain rule, and the chain rule will allow that extra x to come out, and the 1/2 is going to take care of the 2 with that. That would also be present. All right, and Mr. Waffler went through some of those in the video. That's why I'm not going super far with this, but hopefully these two you're feeling comfortable with because it's going to get more challenging as we go along. Now, we don't have the time to really write all this down. So if you want to take a screenshot of this, you can. Or let's just look at some tips or steps for doing U-substitution, which remember, U-substitution is just our way of undoing the chain rule. So we're going to set the inside function to u. Now, what we mean by that is if there's something on the inside of parentheses, inside of exponents, if it's the inside of a root, or cube root, square root, anything like that, or if it's in the bottom part of a fraction. Okay, those are all the ways that we can kind of decide which value of u we should pick. And it takes a while. That's the hard thing about this, is students, once you get the hang of it, U-substitution is actually really quick, but you have to get used to the beginning part. So once we find u, then we calculate du by taking the derivative, and then we have to match du and u to the parts of the original problem and substitute them. And then hopefully you get a new integral which is easier. That's the goal. U-substitution makes the integral easier. And then the last part, just make sure you change your values back to x. Okay? Now, like I said, we're not going to spend time writing that. We're just going to keep that in mind. And I'm going to make reference to these steps as we solve these problems. Okay, so let's look at some more tricky problems, but once you get the hang of this, I hope it's friendlier. And we'll do one at a time here. All right, our goal is to evaluate or solve the integral. The first thing is this 5th power. Now, what I would do with this problem is I don't love this cosine times sine to the 5th the way it's written, because I don't really see the inside function here. So remember that 5th power can be rewritten like this. This is sine to the 5th power. Well, now we're going to let u equal the inside function, right? So what's the inside function? Sine is inside the parentheses. Okay, that's a big piece. If you can understand what the best u is to pick, then you're on the right track. Now that we have u, we're going to take the derivative of u, and that's what du stands for, right? It's the derivative of u. So what's the derivative of sine? It's cosine of x dx. Wait a minute. By picking the sine, we're going to replace this sine with u. So I'll have a u to the 5th power, and then I'll have my integral. But then the du is going to replace the cosine and the x. And notice, I have a cosine and I have a dx. So these two items are going to be replaced with du. And notice, everything was accounted for. The sine was replaced by u, the cosine and the dx were replaced by du, and the only thing that's left is u to the fifth power of our integral. A much easier integral to deal with, and that's the goal of U-substitution. So now I'm going to undo the power rule, meaning I'm going to add 1 up here, so I'll get a 6 up top. If I have a 6 on top, I have to multiply by its reciprocal. And then we're going to put plus c. And just remember, we're not done here, right? Our answer was in terms of x. So now we're just going to replace. And what was u equal to? U was the same as sine of x. And then if this was a multiple choice question, the 6 would be written like this instead of sine squared, but either of those answers are correct. Okay. So U-substitution is designed to make our life easier. And I'll just kind of tell you, we know for sure that I'm hoping everybody, unless you have any health concerns, you're taking the AP test in person. I just think that students are going to do much better with the in-person test than they would with the online test. So what does that mean? That means that in person, you're going to have more problems like this, where you're going to have to show all your steps, which is a good thing. You get more partial credit for things like that. Okay, now here's the thing that's really tricky. Let's look at a problem like this. And you're going to notice something. We have 2e to the x sine squared e to the x. And I want to pick u as my inside function. And so u was the inside function here, was the sine squared. Well, in this case, you can see the parentheses as e to the x. So we're going to go ahead and just let u equal e to the x. And now, notice how there's another e to the x? This isn't a u. This u is different. But where is that e to the x going to go? Well, the derivative of e to the x is e to the x. And don't forget dx. Okay, so now, this dx is taken care of. This e to the x is taken care of. I have everything that's going to be replaced. So the 2, I don't have anything to replace that original 2, so that 2 is going to stay. This e to the x and this dx, let me do that in a different color, is going to be replaced with du. Okay, because I have e to the x and dx, and both of those are present. That e to the x and that dx is going to be replaced with du. And then what's left over? Sine squared of u. The e to the x was the u. So now we do have one option. This 2 is a multiplier, so you can pull that out. And now I'm thinking, okay, I made this integral easier to view with U-substitution. So then I'm thinking, well, whose derivative gives me secant squared? So we're going to do the antiderivative. Whose derivative gives me secant squared? That's tangent of u. And then that 2 is going to drop down because it's just a multiplier. And then we're going to put plus c. And our final answer, instead of u, we have to write our answer in terms of x, or whatever the original problem was. So there I'm going to go back to what I called u and replace u with e to the x. And again, if you aren't confident, take the derivative of your answer and you should get right back to where you started, and you'll see this extra e to the x here That's there because of the derivative of the chain rule. The chain rule is what we did here. So U-substitution undoes the chain rule. Okay. So hopefully you have a couple examples in your notes of what to look for. Now I just want to show you some really quickly so you can just get exposure to the problems. And I don't want you to write these down. Okay? If you want to ever go back and look at them, they're going to be in the notes posted. These are just a little bit of a couple tricky ones that I think it's nice to look at. So I'm going to do them very quick. All right, here's my function. Notice this is in 7 minus 7x minus 11 is the inner function. So that's why I'm choosing this. And then notice what happens. If you ever have a minus 11, that's a constant. And when I take the derivative of that, that constant's going to go away. So the derivative of 7x is 7 dx, and then the derivative of 11 goes away. But notice I have an extra 7 here, and that 7 is not present in the original form. So I have to move the 7 over and bring it with the du, and then this dx is going to be replaced by du. So what's left over? Well, I've got the negative 1. I called the entire inside u, and then dx is going to be replaced by 1/7 du. But instead of writing the 1/7 here, I'm going to pull it out front and then call that du. Now here's a hint. Notice how this is u and this is u. You shouldn't have any x's left over. All the x values are taken care of. Well, now notice this integral is the same thing as 1 over u du, right? U to the negative 1 is really 1 over u, and we know that that antiderivative is the natural log of the absolute value of u plus c. But instead of u, we know what u is equal to. There we go. Okay, let's look at another one. Notice inside function, and then I have an x dx. So I'm going to let u equal x squared minus 1. Du would be the derivative of that. But notice I don't have a 2 here. I have the x and dx. Those are taken care of, but I don't have a 2. So I have to move that 2 over. And now I can replace everything that I wanted. Right? The u was x squared. Oops, sorry. X squared minus 1 is going to be replaced by u. The du, the 1/2 du, the 1/2 is going to come out front. The du is going to replace the x and the dx. So this x and this dx go away by this 1/2 du. And now it's just undoing. We made this easier to look at. So I'm going to undo this power by adding 1. But if I put a 6 up top, I have to multiply by a 6 in front. A 1/6, and then I have 1/2 times 1/6, which is 1/12, u to the 6th, but we don't like that with the u in there, so I'm going to replace u with x squared minus 1. Okay, so I just wanted you to see those because those are just kind of straightforward ones, but it's just good to get a couple of more problems under our belt. This one I don't want you to write because the question always comes up, what if I pick the wrong u? And that's important. You got a question, Emily? No? Okay, cool. I just wasn't sure. Also, let me know if you do have a question. It would be really good to answer any questions as we move along. So right now, if you see this value, you actually see kind of a trick. I've got whose derivative gives me tangent? Well, right now, we don't have any derivative that gives me just tangent. And there isn't an inner function here that's going to make this an easier problem. But what it could do is, what if I think about what tangent is? Right? Isn't tangent the same as sine of x over cosine of x? So all I did was a trig identity and replace tangent with something that it was equal to. And what that gives me now is it gives me a fraction. So watch what happens when I pick the wrong u. That's why I don't want you to write this one down. What if I let u equal sine of x? If I do that, it's going to look like I'm on the right track because the derivative of sine is cosine. But I have a problem here when I try to go in and replace this. Okay, if I do this, sine is equal to u. So I would go up here and I put a u here. And I have my dx. Okay, the dx is there. And I have a cosine. So it looks like I'm in the right spot, but there's a problem. This cosine is a positive value, and this one's down below. So I cannot replace this cosine with this cosine because this cosine is technically a positive 1. And if I was to rewrite this cosine, it would be rewritten as cosine to the negative 1, and those are not the same. So picking the incorrect u value causes conflict. It's not going to help us out. So what does that mean? That means I actually picked the wrong value. And sometimes you do that, especially early on. You don't know which one is best. But what happens if I pick cosine? So if you have a fraction, it's usually recommended to try the bottom one first. It's not always going to work, but most of the times it does. Because now watch what happens. The derivative of cosine is negative sine. Of dx. And what do I have? I have sine, which is positive, and dx. I have both of these represented right here. That is my du. The only thing I don't have is this negative. So I'm actually going to divide by a negative 1, times by a negative 1. So then when I replace the du, I'm just going to think of this as like a negative 1. I'm just going to push a multiplier of negative 1 out. And what's left over? Technically, I have a 1 left over cosine, but cosine was u. Okay. Now, I do want to show you this. Sometimes it can be rewritten where the du, instead of written down there on the side, they just put du up top. And if you see that, I want you to just think of that as 1 over u du. You can always push the du off on its own and just put a 1 up there. Okay. Well, now, whose derivative gives me 1 over u? That's the natural log of u plus c. And then all we do is replace u with what it's equal to, which is cosine. Okay. So this one was just a tricky one. I wanted to show you that picking the correct u value is key. Okay, so we've got one last thing. Definitely write this down. U-substitution and definite integrals. Everything we've done so far hasn't had any bounds to it. Now, this is where I think you're really going to like U-substitution because it actually makes the indefinite integrals, the ones with bounds, it makes this a lot faster. Okay. Now, you'll notice we still have a function 2x plus 3 being squared. So I do have that inside function. And that's going to be my u. Because right now I couldn't do this without U-substitution. So we're going to let u equal 2x plus 3. And then we're going to take the derivative of u just like we always did. So that's the derivative of 2x is 2 dx. And you'll notice I have a dx, right? But I don't have a 2. That 2 is not present. This 2 is already belonging to the u, so I don't have an extra 2, so I have to move that 2 over to the other side. So I'm just going to divide by 2. But now I have something equally to replace pieces with. So I know that 2x plus 3 is going to be replaced by u. I know that 1/2 du is going to be replaced by dx. So instead of writing the 1/2 here, that's a multiplier. We can push that to the outside. And then I have du. So technically nothing new, right? But here's the important part. We have to change the bounds. So these bounds right now are in terms of x, okay? Because that's the original problem. We need to change the bounds, and I usually draw an arrow like this. And maybe for your notes, let's write in blue, this is change the bounds in terms of u. Okay, and Mr. Waffler showed you this in the video, so you might already know it. But if I take this 4 and I plug it in, I'm going to do 2 times 4 plus 3. So all I did was take the u and say, well, 2 times 4 is 8. 8 plus 3 is 11. So this is my new upper bound. Okay? Or sometimes I just write top. So that's going to go right here. And then you have to do the same thing with the bottom. And we're just plugging in, if u was 2x plus 3, we're just going to plug in 2 times negative 2 plus 3 and evaluate. So we get negative 4 plus 3. And there's my new lower bound. Now here's the benefit to doing this. Once you change the bounds in terms of u, you don't ever have to go back to your x's. And that's the nice part about this, is that it actually, you did the conversion. So now we're just going to deal with everything else is just in terms of u. All right, and let me know if there's any questions that you had right here. This is a great time to ask a question. Because if you can get where we got here, then we're in a good spot. Okay, so now we have to evaluate this integral. Well, whose derivative gives me u squared? I'm going to add 1 up top, so that'll give me a 3. And if I put a 3 up top, I have to put a 1/3 there. Don't forget about your 1/2. That 1/2 is just multiplying this. And now look at the notation. Okay, I didn't do anything with the bounds yet, but I took the antiderivative. So now I have to evaluate from the top bound to the lower bound. And here's a hint. If you ever do U-substitution and you get a smaller number up top, just leave it. It's all going to work out the way that it should. So whatever your new upper bound is, leave that as your upper bound. And then whatever your lower bound is, leave that as your lower bound. Okay, so I know that 1/2 times 1/3, this is 1/6. And you have an option if you want. I'm actually going to choose to do this, right? This is 1/6, and then that's going to multiply by my answer of the upper bound minus the lower bound. Well, what was the upper bound? That's 11. What's the lower bound? That's -1. And now, unfortunately, that's going to be a huge number, 11 to the 3rd power. I didn't have that set up super friendly. And then I know -1 to the 3rd power is -1. So addition, if If I times that by 6, we get an actual answer. Okay, and just like we saw before, when you have definite integrals, you're not putting the plus c, and maybe that was a question that you might have had right away. Where did the plus c go? The bounds take care of the constant, and you're just left with your answer. All right, we got 2 more for sure that I want to get to. And yep, this is a good one for us to do as well. I see a lot of these style questions on the AP test. So same directions, evaluate the indefinite integral. Now eventually, we're not going to tell you to use U-substitution. You just have to know that you have to do it. And that's where it really gets hard, is when they don't tell you that you should use U-substitution. But we want to pick a U. It's a fraction, and there's 2 ways that I know the correct U value. You want to pick a U that's in the denominator, but you also want to pick the U because if I take the derivative of x squared, I get 2x dx, and notice how that x and this dx are present in the function as well. So I have an x and a dx, which are both right here. The only thing that I don't have is an extra 2. And that 2 just moves over to the du. And now you see exactly the x dx. That's going to be replaced by the 1/2 du. So I usually write the 1/2 out front. And then the bottom, this whole bottom is just u. And if I replace the x dx and the 1/2 is out front, I like to write the du in the bottom, then you can always put a 1 there. Okay? So again, nothing new, right? This is what we just talked about, but here's the new part. I have to change the bounds. Because it's the indefinite integral, we're going to change the bounds in terms of u. So I'm going to take whatever u was for the upper and the lower, and we're just going to plug in 1 and 0. So upper bound and lower bound. So here I get negative, so 1 squared minus 4 is negative 3. My upper bound. 0 minus 4 is the lower. And again, I don't care what these numbers are, right? If this one was really small and this one was really big, I don't care. I'm going to put them exactly where they're told to go. So the upper stays the upper no matter what the number is, same with the lower. I don't care about flipping the bounds anymore because we're just doing the antiderivative now. All right, so now I'm looking at this, well, 1 over u, whose derivative gives me 1 over u? That's the natural log of the absolute value of u. And then I'm going to draw that line. Maybe I'll do that in red so we don't get that confused. And I'm going to go from negative 3 to negative 4. Okay? And now, because we changed everything in terms of u, I don't ever have to go back to replacing this u. So I'm just going to leave it, and we're going to take the natural log of negative 3. Notice it's the absolute value, minus the natural log of negative 4. And then I just times everything by 1/2 at the end. Now this is interesting. I would tell you to stop right here. This is an acceptable free response question answer. However, What if we use the absolute value to turn that to a positive 3 and a positive 4? Okay. And then this is the part kids don't love, but we had a property that said in pre-calc, if I had the natural log of 3 minus the natural log of 4, that can be rewritten as a division. So this is what the multiple choice question would look like, most likely. And it's just a pre-calc property from here to here. And I know it's not awesome, but if you want it a little more general, this is what the pre-calc property is right here. All right, one last one. I know it's been a lot today, but I love this problem because it gets at the essence of what you're going to be doing. And I will tell you, you'll see something like this coming up in our future and the AP test. Hint, hint, hint. So it's a multiple choice question. And it says, if f is a continuous function and the derivative of f is equal to f of x, this is basically saying that if I took the derivative of an antiderivative, I get the original function. But they're really telling me this right here. I have to evaluate that, and I want to rewrite it in a more fancy function. Well, I can't do that until I do U-substitution. So what we're going to do is we're going to let u equal the inner part, the 2x. And then du is the derivative of that, so that's dx. But notice, I don't have an extra 2 here, so I do have to move this 2 over. All right, so we're going to rewrite this using everything that we know. Instead of 2x, we called 2x u. And then instead of dx, which I have my dx here, instead of dx, I'm going to replace it with 1/2 du. And then I've got my bounds. These bounds are right now in terms of x, so I need to rewrite them, right? So 2 times 3 gives me 6, and 2 times 1 gives me 2, and here's my upper, my lower, 6 to 2. Okay. Now, if that's not enough, sometimes they have this and then your answers are just this notation. So you just have to match the integral to this. And maybe it's an algebraic manipulation of it. But what do we know? We know that if lowercase f is the function, then its antiderivative is uppercase f of u and we're going to evaluate from 6 to 2. Okay. And then the last part, we plug in capital F at 6 minus the lower bound, which is capital F at 2. And then our goal is to figure out which one of these matches up. You can see part E. All they did in part E was distribute the 1/2. So these are fairly common problems on the AP test because it gets strictly at U-substitution and changing the bounds. And then knowing that if you have an integral, the fundamental theorem of calculus says you take the antiderivative. Yeah, there is a reason why they use the same letter F. or are you saying the U? You could pick any letter other than X for your U. It doesn't matter. But the reason why they use capital F and lowercase f is this lowercase f is the function, and then capital F is the antiderivative. And that's just the way notation is brought up. So I know it's tough. It's not easy. Okay, we'll do this one probably as a warm-up. I just wanted you to really quick look at it, and I'm not going to do this, but notice, what would you pick for your U? You should pick secant of x. And the reason why is look at the derivative. The derivative of secant, oh, I'm sorry. No, hold on. I picked the wrong one. This one is actually kind of interesting. What should the U value be? Well, you have two options. Is it secant or is it tangent? And if I pick U to be tangent, notice the derivative of tangent is secant squared. So you can see right here, du is going to replace all of this. So there's du. And then this integral would be tangent is u du. And then you just need new bounds. So I'm not going to do this one. I just wanted to show you which u you should pick. So you would go there. Okay, here's what we got for homework tonight. Homework is in the textbook, and I want to make sure you guys know that we want you to copy the original integral and show all of your work when you're doing U-substitution. Practice that work. All of these answers are in our worked out solutions. I already did them and put them in our homework answer section, and I did that because I know this isn't easy, but you can go and check. For the red ones, only do U-substitution. So use those directions for the red one. The directions they give you, they have you do it two different ways. I just want you to practice U-substitution. Okay? And I think the last problem or two gets into the conceptual understanding. So make sure you do that. And please make reference to my answers as you work through it. Okay? I will be available in my office hours from 1 to 2 today. So if you have any questions on this material, if you didn't watch the video from Wednesday, you should definitely watch that. And if you have any questions on the test that we just took, please stop in. We can go over any of that. Adios. Have a good day.
Mr. Stroh, I
Yes.
actually had a quick question.
Sure.
So 2-3 slides ago, you were talking about like